Alright, welcome back guys. We're going to be covering section 7.4 as you can see, and we'll spend a bit of time in this section guys. It's quite important. There is a support section for it, and the support homework is really just like the 7.4 homework. Okay, so this really just deals with solving quadratic equations, or in other words, they also call that finding the zero of the function. We'll talk a little bit more about what that means, but we've looked at solving one-dimensional equations before. So for example, if you had 2x minus 1 is equal to, well, we'll say 7. Okay. You can solve an equation like this simply by isolating the variable. So, in performing inverse operations, so you could add 1 to both sides of the equation. That'll give you an 8 over here, and then you could divide both sides by 2, and then you get x is equal to 4, I believe. Okay. So anytime you have an equation and there's a variable, and that variable is just to the first power, you can always solve it by isolating that variable. However, with a quadratic equation, so a quadratic equation arises when you take a quadratic function and you set it equal to something. If it's got that equal sign in it, okay, like I'll show you an example. Down here would be an example, okay. It's got an equal sign in it, so it's an equation. We don't call this a quadratic function, we call this a quadratic equation. A quadratic function would just be basically the left-hand side. So like v squared, or it could be x, it doesn't matter. Minus 6v minus 27. Okay. So notice this is the function right here, or expression, the quadratic expression or function. But when we set it equal to 0, the way we've done right here, then it becomes a quadratic equation. And that's what we want to focus on solving in this section. And solving these types of equations, guys, is not as simple or straightforward as solving an equation in one variable. Okay, one variable to the first power, a one-dimensional equation. In fact, it's a little more. Just a second, my computer froze. Gosh. Okay. Alright, well, I'm back and appear to be moving. Okay. So, so I was saying solving these quadratic equations takes a little more ingenuity. Okay. And that's what we're going to kind of go over. Now, there are really 3 different ways that you can solve them. One way is by factoring. And I'm going to spend some time going over how to solve quadratic equations by factoring. But the issue is that not every quadratic equation can be solved by factoring. And then there's some quadratic equations that can be solved by actually isolating the variable. And we'll look at those. And then we'll look at a third method that will work for any quadratic equation. And that's what we're going to try to focus more on from here on out. Okay? But factoring is a process that's very important, not just to be able to solve quadratic equations, okay, but for other things in math as well. And so I will go over a few problems in which we do some factoring. Now, in college algebra, you're expected to already know how to factor, okay, but the reality is, I understand most students probably have forgotten that. They may have been proficient in it at one time, but likely have forgotten it when they actually take the course. Okay, so I may also add a couple extra, a couple other videos that are not mine that covers factoring as well. Okay, so first let's talk about a quadratic equation in standard form. Well, actually, let's look at a quadratic function. So a quadratic function, and we've talked about this, we've seen a lot of quadratic functions. Okay, f of x is equal to, if you remember, that basic quadratic function is just x squared. But we can also have an x term and a constant term, and it's still quadratic. Okay. In fact, guys, the standard way to express a quadratic function is like this. Okay, where you have your x squared term. You may or may not have an x term depending on whatever this number b represents, and you may or may not have a constant term depending on the number that c represents. Okay, so this just says where a, b, and c are real numbers. Okay, so in other words, they're coefficients. And so to obtain this basic quadratic function, evidently b and c would have to be 0 for these two terms not to show up. Okay. But most of the quadratic functions that we're going to encounter today, b and c are going to be in there. Okay. And we also, if you notice, we like to write it in what's called descending order, such that this x squared term comes first, the x term comes second, and then that constant term is third, okay, if it has one. Now, when we have, and here's an example of a quadratic function written for you, x squared minus 8x minus 20. In this case, the value for a would just be that little understood 1 that's in front of the x squared. The value for b would be negative 8, and the value for c would be negative 20. Okay, so when we have a quadratic function like this, we can set it equal to something, and if it's set equal to 0, then we say that it's a quadratic equation in standard form. Okay, so sometimes you might see a quadratic equation and it's not equal to 0. It could be equal to some other number, or there could be some x terms on the other side. That would still be a quadratic equation because it contains an equal sign, but it wouldn't be in standard form. Okay, standard form has all of your terms on the left-hand side and 0 on the right-hand side. Alright, so what we want to focus on now that we've talked about what a quadratic equation in standard form looks like is if we had a quadratic function and it was equal to 0, how would we solve it? Okay, how would we figure out the value for x that makes this a true statement? You know, when you have an equation like this, guys, you could almost solve this one by guess and check, trial and error. Substituting values in for x, multiplying by 2, subtracting 1, and see if they give you 7. When you have a more complex quadratic equation, that trial and error method is not going to be very efficient. Not that it ever really was to begin with. Okay. All right. Well, one way looks like I've frozen again, but that's okay. One way to do this is by factoring. If you can express the left-hand side as a product of two factors, and those two factors equal 0, then that must mean either both or one of those factors is 0. That's actually this principle right here, okay, this principle of zero products. The principle of zero products says that if you have a product, okay, remember product means multiplication. So in other words, if two things that are being multiplied equal 0, then we can infer from that that either the first factor, and by the way, each of these pieces is a factor. Okay. The factors are the pieces that you multiply together to get the product. So if you have two factors and their product is 0, then that implies that either the first factor had to have been 0, or the second factor had to have been equal to 0, or they both could have been equal to 0. Okay? This should really say and or right here. And or. Okay? This is similar to me saying I'm thinking of two numbers such that when I multiply them, I get 0. Can you tell me anything about either of those two numbers? Well, most people intuitively would say, well, one of them has got to be 0. Otherwise, you're not going to be able to multiply and get 0. Or they could potentially both be 0. Okay? And so the way this principle here applies to solving these quadratic equations is that if you have a quadratic equation and it's equal to 0, if we can factor the left-hand side into two pieces, then we can set each of those pieces equal to 0, and we can solve that equation. Okay? And I'll give you an example right here. I'll kind of walk you through it. And then we'll do one, I'll do one for you. Now when you're thinking about factoring a quadratic equation in standard form, there's going to be two cases. There'll be a case when there's a number other than 1 in front of the x squared, so case 1. And there'll also be a case 2 whenever there is a number other than 1. Okay? An example of this would be right here. Okay? See, there's a 3 in front of the x squared. Notice this equation has an understood 1 in front of the e squared. This one right here also has an understood 1. Okay? So quadratic equations with all three terms, this is called the leading coefficient. Okay? We say, if there's not a number right there, we say this is a quadratic equation without a leading coefficient. So when it doesn't have a leading coefficient, they're easier to factor. So if I'm looking at this, okay, we're not going to set it equal to 0 initially. We'll just focus on how would we factor this, or in other words, what would we have to multiply to get these three terms back? Well, it turns out they end up becoming binomial factors. Okay, so in other words, binomial, that means a polynomial that has just two terms in it. So if you're thinking about this, you're basically doing the opposite of foiling. Okay, instead of multiplying two binomials together, you're trying to figure out what must I have multiplied such that I obtain this quadratic right here. Okay, so for case 1, you're going to need an x times an x. That's the only way you're going to get back your x squared here. And then the only way you're going to get back your negative 20 is you need two factors that when multiplied give you negative 20. But also when added together give you negative 8. Okay, because that's the process when you FOIL. You do first, outer, inner, last. And the outer and inner terms, you add them together. And so when you add them together, they need to give us a negative 8 right here. And so you figure out that usually people will make a little chart. They'll say, okay, I'm trying to think of two numbers that when multiplied give me negative 20, but when combined give me negative 8. And so there's only going to be one choice. It's negative 10 and positive 2. Those multiply to give negative 20 and add or sum to give negative 8. And so once you determine what those two numbers are, you simply plug them into your binomial factors. And now you have it in factored form. Okay? This is kind of like your A times your B. And if A times B equals 0, then that means either A, x minus 10 equals 0, and or B, which is the second factor, x plus 2, is equal to 0. Okay? And so what you do is you take your two factors, you set them equal to 0, and you solve them for x. And so if I were to do this right here, if from this one I would get x is equal to 10, because I'd have to add 10 to both sides, and then from this one I would get x is equal to negative 2. And so we actually end up with two solutions. And this is very common with most quadratic equations, because it's a second degree polynomial, or in other words, because it has an x squared, you typically will obtain two solutions. There's actually two numbers that'll make this left-hand side equal 0. Okay. All right, so let's try one on our own. This example 1 right here. Let me zoom in. And guys, I kind of said all of that right in here in the notes. So if it's in standard form, then A is an understood 1, B is just the number in front of your middle term, and C is your constant. Okay, so that's what I mean when I say C is equal to negative 20, B is equal to negative 8, and you're trying to find factors of C that sum to negative 8, or that sum to give you whatever B is. And those factors are negative 10 and 2. And like I said, I do usually use a factor chart. Okay. Alright, let's try example 1. Alright, so here we've got a quadratic equation. It's in standard form because it's set equal to 0, so we need to try to solve it by factoring. Okay. Now again, let me point out, these can be factored, but not all quadratic equations can be solved by factoring. Okay. But when we look at that third method later on, even though a quadratic equation can be solved by factoring, it can also be solved by that universal method. Alright, well this one is v squared minus 6v minus 27 is equal to 0. So we know the nature of the factors. They're going to have to be binomials. Okay. And we would need a v times a v to get back our v squared, and then we would need two numbers that when multiplied give us negative 27, but when combined give us the middle coefficient, negative 6. So I will make a factor chart. Okay, so what times what gives me negative 27? Well, there's a lot of numbers, okay? Negative 9 and 3, positive 9 and negative 3. What about 27 and negative 1? Or negative 27 and positive 1? Okay? These are all combinations. These are all factor pairs. But only one combination will combine or sum to give us negative 6. And that's the first one. Okay? And so those are the values, the two constants that we're going to use in our two binomial factors. Okay. So again, I have factored the quadratic function. So now I have the product of these two factors equals 0. So that means that either one or both of these have to be equal to 0. And so we take each one individually, we set it equal to 0, and we solve for v. Okay. Here, you know, we need to add 9 to both sides. And so we get v is equal to 9. So that's a solution. And then over here we would subtract 3 from both sides. And we would get that v is equal to negative 3. So both negative 3 and 9 are solutions to this quadratic equation. Okay, so you can say v is equal to negative 3, comma 9. Don't write this as an ordered pair because that's not what it is. These are two values for v, or x, or whatever the independent variable is, okay, that solve your equation. Now, when your quadratic function is set equal to 0, when you find these values, you're not only solving the quadratic equation, you're also finding what are called the zeros of the function, because the function is just the left-hand piece. And to find the zeros of the function, you're essentially finding the values that make it equal to 0. Okay? So this whole process of solving these quadratic equations, another way to put it would be we are finding the zeros of the quadratic function. And I'll show you what that means graphically later on as well. Okay. All right, so there's an example of a quadratic equation that's missing the leading coefficient. What about case 2? When there is a leading coefficient, okay, and it's not 1, it's some other number. Well, those require a little extra work. Okay. Most students aren't too fond of them just because they're kind of time-consuming. All right, so case 2, to factor a quadratic equation that has a leading coefficient that's not 1. Okay. So like this one, for example. Well, what you do is you end up multiplying A and C together. Okay, so the 3 and the negative 7, and you get negative 21. And so that's the number that you try to find factors for. So part of this process is the same as the last case. So what factors of negative 21, when combined, will give me this middle coefficient, B? Negative 4, in other words. Well, those factors are negative 7 and 3. If I multiply negative 7 by 3, I'll get negative 21. And if I add negative 7 to 3, I'll obtain negative 4. Okay? And so, where do we go from here? Well, I want to point out that to factor something like this, let me rewrite it real quick. Okay, you forget about the equals 0 part for a moment because you're just working on factoring this one. These factors are going to be binomial, and they will involve these two numbers up here that we just found, negative 7 and 3. But it's not going to simply be x minus 7 times x plus 3. Okay? This would work if the 3 wasn't there. But when it has that leading coefficient, this doesn't work. And you can see this because x times x is not 3x squared. Okay? And so what you have to figure out is what times what gives us 3x squared. The negative 7 and the 3 will give us, wait a minute. Yeah, well, the point I'm trying to make here, guys, is that the negative 7 times the 3 are not going to give us negative 7. Okay? And so this approach that we had previously is not going to work. So what we do is we do something called factor by grouping. And what I mean by that is we rewrite this middle term, or we re-express that middle term using these two numbers right here, okay, from the factorization. So we rewrite the first term, we rewrite the last term, but we re-express the middle term using these two numbers. So instead of writing negative 4x, we write negative 7x plus 3x, okay, utilizing these two numbers. And each of these terms needs an x, because if you were to recombine them, you still need to be able to get that negative 4x back. So all we're doing, we're not changing this in any way. We're just modifying the way it looks. Okay, and that's all. We want it to have 4 terms, because to perform this factor by grouping method, we group each of these 4 terms into pairs. Okay, so for example, we group up the first 2 terms. You put them in parentheses. You're always going to put a plus sign between your 2 pairs. And you group up your last 2 terms, keeping them in parentheses. Okay. And then what you do is you, from each of these groups, you extract what's called a greatest common factor. You may have heard of that before. It's basically, what do these two terms have in common? Okay. Well, the 3 and the 7 don't have any common factors. But the x squared and the x, they both have an x. So in other words, each of these two terms here, they each have at least one factor of x. So you factor that out. And so if you take out that x, then you're only going to have 3x in your first term. It won't be 3x squared anymore. And then your second term, you're only going to have a minus 7, because the x won't be there. You factored it out. Factoring, again, is the opposite of multiplying. So instead of distributing the x, you're basically dividing it out from these two terms. Okay. And then you go to your second pair, and you think, okay, what do these two terms have in common? Well, looking at them, you may say nothing. They have nothing in common. But they always have something in common, and that something is either a positive or a negative 1. Okay? In this case, it's going to be a positive 1. So in other words, if I were to take out a positive 1, what would I have left? Or in other words, if I've gone back and divided each of these by positive 1, well, they're going to remain the same. That's what happens when you divide by 1. Okay. You get 3x minus 7. And so then what you do, you notice that you've got a binomial in here that occurs twice, a 3x minus 7. Okay. So you then factor that out. That is the greatest common factor in these two larger terms. Okay. See how they're separated by addition right here? So you take out the 3x minus 7, and then you plug in your second set of parentheses what you have left. So the way I typically show this is, once I factor out the 3x minus 7, all I'm going to have left is an x and a plus 1. And that's what I plug in my second binomial. X, oops, and a plus 1. Okay? And now you have it factored. And you can even check it. Anytime you're factoring, guys, you can always go back and check by multiplying. So 3x times x, that would give me 3x squared. 3x times 1 is 3x. Negative 7 times x is negative 7x. Okay, like what we had here. These two terms would combine to get me back to negative 4x squared. And finally, negative 7 times 1 is negative 7. So this works out. This is the factorization. And then to finish this off, you remember that it's set equal to 0. And you take each of your factors, you set them equal to 0, and you solve, in this case, for x. Okay. So the process of factoring these quadratic functions that have the leading coefficient, and it's not 1, is a little bit more complicated. You have to use the factor by grouping method. Okay, so let's do one on our own, and then I'm going to stop this part 1 video, because we're already close to 30 minutes. Alright, so this one right here, it's already in standard form. You can see the leading coefficient is 2. So we're going to have to factor it by grouping. So what that means is we'll multiply a times c first. So I usually just show this with an arrow. 2 times 14 is equal to 28. And we need to find factors of 28 that when combined will give us negative 11. Well, those two factors are both going to have to be negatives. They're going to be negative 7 and negative 4. Because when you multiply two negatives, you get the positive 28. And when you add two negatives, you get the negative 11. Okay, and so now I proceed to factor by grouping. So I drop down my first term, and I split up my second term using these two pairs of factors that I just found. Minus 7n minus 4n. Remember, each term has to have a variable, because if you were to combine them, they still need to give you back that initial term. And then you drop down that last term, plus 14. And now you start factoring by grouping. So we do this one the same way. Group up those first two. Now, I told you always want to put a plus sign in between your two groups. So if this third term has a negative, the negative needs to go with the number, follow the number. Okay, it's part of the number. And then you'll have plus 14. It's very crucial. So I've got them grouped up now. So from each of these groups, I'm going to pull out a greatest common factor. So the only thing that I can see that these first two terms have in common, again, is just an n. Okay. And so if you were to go back and divide the n out, you'll only have 2n from the first term, and you'll only have a minus 7 from the second term. Now let's go to the second group. So these two terms don't have an n in common, because only one term has n. However, the coefficients do have a number in common, and that number is 2 or negative 2. Now, how do I know which one to pick? Well, we want what we obtain in our second binomial here, or this binomial here, we want it to match what we have in the first one, because ultimately we factor that out. So if I take a positive 2 out, then my signs aren't going to match. Okay? So I take out a negative 2. And to see this, you can literally divide them by negative 2. So here, these two negatives become a positive 2n. And 14 divided by negative 2 is negative 7. And so now you can see that this factor matches this factor. Okay? So I have this binomial factor common to both of these terms. So I take it out, I factor it out. And so what does that leave me with? Well, if I had factored it out, then it would be gone from each of those terms, and I would only be left with the n and the minus 2. So that's what we plug into our second binomial factor here, n minus 2. Okay? And then we remember that it's equal to 0, but now I have it factored. So now I can set each of these factors equal to 0, and I can determine those values for n. Okay, so I'll do this over here. Take my first factor, set it equal to 0, and then my second factor. And so here, we would add 7 to both sides, and then divide both sides by 2. So we would get n is equal to 7 halves. And then over here, all we need to do is add 2 to both sides. So we get that n is equal to 2. And those are our two solutions. Or in other words, those would be the two zeros of the quadratic function, okay, if it weren't set equal to 0. In other words, these are just the values of n that make this guy equal 0. 2 and 7 halves, which is the same as 3 1/2. Okay. All right, well, I'm going to stop part 1 there. I showed you a couple of examples of how you can solve the quadratic equation by factoring, but a lot of quadratic equations are not factorable. Okay. So when we come back in part 2, we're going to look at quadratic equations that are missing the middle term or the x term. Turns out we can solve those directly for x, and it's called using the square root method. Okay, so we'll see that in part 2.